Hello all, myself Ravi Rasi Chauhan. In this video, we are going to cover structures of the page table. Let us understand what is page table first. So page table is the memory management unit which converts logical address provided by CPU into actual physical address of the memory. Every process maintain their own page table, and the page table is stored in the main memory. So let us calculate the page table size. How to calculate the page table size? For any kind of memory, the size of that memory is number of entries into each entry size. Now how many number of entries are there in the page table? It is same as number of pages in the logical address space. So the page table size is calculated using number of pages, that means number of entries into each entry size. Let us consider the scenario of 32-bit logical address space, so as we have in the modern computers, and the size of the page is 4 KB. So how many entries are there in the page table is 2 raised to 32 divided by 2 raised to 12, that is 2 raised to 20. Means we have to enter 2 raised to 20 1 million pages in the page table. If we consider the entry size is of 4 byte, then the page table size will be 4 MB. 1 M into 4 byte, that will give you the 4 MB, and it's a huge amount of memory because we need to store this in the physical memory, right? So it will cost a lot to store this much amount of memory, and we don't want to allocate this memory continuously in the main memory. So we need to reduce the size of the page table. So how to reduce the size of the page table? By increasing the page size. अगर हम पेज टेबल की साइज डिक्रीज करना चाहते हैं तो हमें नंबर ऑफ पेजेस कम करने पड़ेंगे. नंबर ऑफ पेजेस कम करने के लिए हम कैसे कर सकते हैं? अगर पेज की साइज हमने इंक्रीज कर दी तो ऑटोमेटिकली नंबर ऑफ पेजेस रिड्यूस हो जाएंगे, बट इट इज नॉट the desirable solution. Why? Because it will increase internal fragmentation. Let us have one example. For example, program is of 1024 bytes, and if we consider the page size 2 bytes, means smaller page size, then number of pages 1024626 bytes divided by 2 bytes, that will require 513 pages, but internal fragmentation is of 0 byte. There is no memory loss. If we talk about the another scenario of taking larger page size, for example 1024 bytes, so to store 1026 bytes program with page size of 1024 bytes, number of pages required is 2 page. One page is having 1024 byte, and the second page, the remaining 2 bytes will be stored in the second page. So in the second page 1022 bytes will be the loss, memory wastage. So that is called as internal fragmentation. So increasing the page size is not a desirable solution. So what is the desirable solution? We will use different structures. There are 3 different possibilities. One is multi-level paging, that is hierarchical paging. Another is page tables, and the one more is inverted page table. In this video we will see a multi-level paging, and the remaining 2 will be covered in the next video. So what is multi-level paging? Multi-level page table: we will break a logical address space into multiple page tables. In the normal simple paging we will have only single page table, while we don't want to allocate that much amount of memory in a continuous manner, so we will divide that into multiple tables. We will see. So a simple technique is 2-level page table. So we will see what is the meaning of 2-level page table. So actually this is the physical memory, and now page table is divided into 2 parts. One is outer page table and other one is inner page table. Outer page table contains the pointer to the inner page table. Inner page table contains the actually frame number, because in page table we will store the frame number of the main physical address space. So outer page table contains the pointer to the inner page table, and inner page table contains the actual frame number. So Now how the address will be translated from logical address to physical address, for that let us understand one example. For example, we have logical address space 32 bits and the page size is of 1k byte, fine, and it's a byte addressable memory. So number of pages consisting are, so 2 raised to 32 divided by 2 raised to 10, so number of page number is 22 bits and a page offset is 10 bits. So if we talk about normal paging, it required 2 raised to 22 entries, so it is very difficult to store that. So what we do, we will divide that again into two parts. One part is of 12 bits, the size of the outer page table, and the next one is the 10 bits, that is page offset. It is not page offset for the actual data, it is page offset of the inner page table. It is the entry of number of bits of inner page table. So the logical address is divided like this. Your 22 bits of page number is now divided into 12 bits of outer page table and 10 bits of inner page table. For example, outer page table is having 12 bits, so how many entries are there? 2 raised to 12, and inner page table are having entries 2 raised to 10. So now rather than storing 2 raised to 22 entries in at one space, we will divide that into two parts. So P1 is the index into outer page table and P2 is the displacement within the page of inner page table. This method is also called as forward mapped page table. So page table 1 contains entry of page table 2, page table 2 contains entry of page table 3, so it goes in forward direction, so it is called forward mapped page table. So the address will be translated like this. So P1 gives you the exit entry of the outer page table, from that you will get P2, and that P2 gives you the exit entry of inner page table, and in inner page table we will store the frame number, and that frame number plus D gives you the physical address. So now this is the actual change of multi-level paging. In simple paging we have only one page table here. In multi-level paging we have multiple page tables. The only thing is the last page table is actually contains frame number. The remaining page tables are containing the pointer to the next page table. So let us talk about another example. If we talk about 64-bit, right now we are using 64-bit logical address space system, right? So even 2-level paging is not sufficient. The reason is, if we talk about page size, our page size is of 4 KB, then also it required 2 raised to 52 entries. If we talk about 2-level scheme, and if inner page table, we can store 2 raised to 10 of entries of 4 byte. If we talk about each entry size is 4 byte, and if we want to store 2 raised to 10 entries of inner page table, then the inner page is of 10 bits, and the out of 52 bits the outer page table is of 42 bits. That also required 2 raised to 42 entries. And if we talk about in terms of bytes, each entry is of 4 byte, 2 raised to 42 entries, so total size of that outer page table will be 2 raised to 44 byte. That is even more. So what we can do, if our page table size is greater than a desirable requirement, will divide into another page table. So one more solution is adding the second outer page table. But in this example, if we add second, that also will not solve our problem, because if it's second page table of 10 bits, then also it is having 32 bits, so 32 raised to 34 bytes in the size. And if we increase number of levels, it will increase the memory access time, because every page tables are stored in the main memory. So to access one physical memory, we have to access 4 times memory, because if 3 levels of page table and 1 is for actual memory access. So this is the 3 level. If we talk about 2-level paging, outer page table 42 bits, inner page table 10 bits, and offset is actually page location, actual data. If we talk about 3 levels, then we may increase number of levels, but it is not desirable to go to increase number of level at any cost, because it is wise complementing each other. If we increase number of levels, it will increase the access time. So we need to maintain the balance of size as well as time. So the how to calculate effective memory access time, like we have calculated in simple paging and paging with TLB. Now if we talk about multiple paging, the simple statement is, if page table size is greater than the desired size, our requirement, then we will create one more level as per our requirement. So in multi-level paging, whatever we store, whatever number of levels we increase, it will be stored in the main memory. That is the important point that we have to note. हमें ये नोट करना पड़ेगा कि ये important है. So it required more than one memory access through physical address. So how many memory access required? One access for each level. जितने भी लेवल्स होंगे हर एक को एक बार आपको एक्सेस करना पड़ेगा, प्लस one time for actual physical memory. So the effective memory access time, if you talk about simple paging of n level, then it is n plus 1. N is for n page tables and plus 1 is for actual physical memory, and m is main memory access time. If we talk about, we can speed up this time and we will use TLB. So it is as it is, x is the hit ratio. If the page is available in the TLB, we don't require this much amount of memory. We have to access C for the TLB plus one time memory access. But if it is not there in the TLB, that is TLB miss 1 minus x, it accesses one time TLB plus n plus one time main memory, because n for the normal number of levels and one is for actual physical memory. So this is the general formula if we consider n levels. If we consider two levels, we put n equal to 2 in this formula and we will have the specific formula 3, 4. We can design the formula for any number of levels and we can solve the example. Okay, so this is how we can use multi-level paging. Now for this video, for this content, let us have questions to check whether we understand this concept properly or not. So question number 1 is, let us consider the virtual memory system with physical memory. Physical memory is 8 GB, a page size is given 8 KB, virtual address space is given 46 bits. So from this we can find logical address space. Virtual and logical both are similar words. So assume every page table exactly fits into single page. So what is the page table size? Page table size is given. If it exceeds this page table size, we will increase the level. So from the page table size is one page. So one page size is 8 KB. So we can say page table size is 8 KB. If it increase 8 KB, we will increase the number of levels. So if page tables entry size is 4 byte, then we need to find how many levels of the page tables would be required. So try to solve this question. If you have any doubt, ask me your query in the comment section. The second question is the similar one. We will consider the 2-level paging. First attempt question 2, then go for question 1. The outer page table is address with the 12 bits. The inner page table is 9 bits. Physical address space is given, number of frames are given. So physical address space and number of frames will give you the frame size. Once you have frame size, you have a page size, and from that you can find logical address space, logical address, and from logical address you can find logical address space. From the outer page table size, if you want to find outer page table size, you have to find, you need to have number of entries into each entry size. So number of entries you can find from this bits, and entry size is of 4 byte. You can solve this example easily. So the last example is little bit tougher one. If you want to attempt it, it's a good example. It's a general example. Consider a logical address space is of s bytes, a page size is p bytes. We need to find the optimal page size. What can be the best page size so that it will not increase internal fragmentation, because if we increase a page size beyond some limit, it will give you the internal fragmentation. But if we reduce the page size, your page table size will be increased. So we need to maintain balance. So what can be the optimal page size that we need to calculate? The page table size entry size is e bytes. So total page table size is s by p into e. So this we need to reduce. Let us assume the internal fragmentation is of p by 2. जितनी भी पेज साइज है उसमें से हाफ पेज वेस्टेज होता है, ऑन एन एवरेज हाफ पेज वेस्ट होता है, ऐसा हम कंसीडर करके चलते हैं. So what is the optimal page size? For that I am giving you the hint, the differentiation. We need to find the differentiation and the page table size and internal fragmentation. We need to maintain balance between these two. So you can solve this question very easily. The last question is little bit a tough one. Please try to solve it. If you have any query, ask me in the comment section, or you can ask me in the personally. Thank you. We will cover the other two methods in next video. Thank you so much.